Good morning, everyone. Hope you're all doing well. So, we are getting really close to the end of the semester here. Really, really close, right? We've got like 2 weeks and like some change. Let's take a look at the syllabus just so that no one is getting freaked out by like how things get sort of stacked up at the end of the semester. So, where are you? So this week we'll be going over acids and bases, which is the last chapter of the semester. You have your fourth test, your final test, this Sunday, Monday. So make sure you get that done. I will obviously remind you again on Monday to make sure you get that done by midnight. It will cover 3 chapters, so it'll cover gases, solutions, and acids and bases. I actually think that this test is slightly easier than the one before it, but you still, it's harder than the first 2, so you still want to study for it. Then the following week is sort of just like a final exam review. It'll be sort of optional. So kind of like, not that lectures have been optional, but some people have come, some people haven't, right? So you'll be able to come log in. I will be here, and we can go over whatever you want to get ready for the final, because the final is cumulative. So it will cover all of this stuff. Maybe what we can do is Monday of next week, we can have that Monday be the first half of the semester, and then we can have Wednesday be the second half of the semester, just so we're not so all over the place. So we'll have Monday be test 1 and test 2, which is everything through like Lewis dot structures and chemical bonding. And then Wednesday will be the chemical reaction stuff, balancing equations, and then all these last 3 chapters. So we can sort of have those isolated. Your final exam is on Monday, 5/10. Let me go to something there doesn't seem quite right. I mean, it seems right that it would be on Monday, but I believe it should be like a window. Yeah, so it's the final exam. It will sit just like the other ones. It'll be Sunday to Monday. Okay, so you'll have almost a 48-hour window to take it. So only a week between that 4th test and the final exam. We good with that? You have 1 lab left to turn in, and some mastering chemistry, so get that stuff done. If you have any late labs, email me and tell me what's going on, why they were late, what happened, and I might be able to give you some partial credit if there's 1 or 2 that you're missing in there. Most of you guys have done really good, though, turning the labs in on time, so bravo. Okay, acids and bases. So we touched on acids and bases a little bit in class, and like how they relate in reactions, neutralizations, and things like that. But let's get more into it. So acids and bases, here's a picture. Acids have been used in spy movies and other thrillers to dissolve metal bars. Do acids dissolve metal? They actually do, yeah. You probably couldn't put enough acid in this pen to dissolve that much metal, but they do in fact dissolve metal. There are certain metals that won't dissolve from acid. Gold is one of them. So we'll talk about how they dissolve metal a little later. Some other things, Sour Patch Kids are a really good example of an acidic thing. A lot of the stuff we eat is acidic. It has a sour taste. So why are we getting that sour taste when we eat something acidic, or like you eat this lemon over here? It's because an acid produces these H+ ions, which sometimes we refer to H+ as, there's a couple different things. Let me get it. All right, all the different ways that we can talk about the H+ ion. Okay, so when we're dealing with an acid, a lot of times it will produce, under a simple definition of it, it'll produce what's known as an H plus. H plus it's a proton. So you may hear them talk about like an acid having something to do with putting protons in solution. Because look at on your periodic chart what hydrogen is. Hydrogen is a proton with a single electron floating around it. There are no neutrons for the most part. So if I have a plus, H plus, that means I've gotten rid of the electron, right? What are we left with? We're just left with a proton. So you might see that as a proton, okay? So those two words can be interchangeable. Another way you might see H plus written, when H plus or an acid is in water, it can actually react with a water molecule to become what's known as H3O plus. This is the hydronium ion, not hydroxide ion, hydronium. This is also considered pretty much the same thing as this, okay? Because there's always going to be water present in reactions. So it can stick to a water and give you this. These two things will have the same properties. So if you see something where it says, hey, the H plus concentration, let's say it has a 3.5 molar H plus concentration, or it says it has a 3.5 molar H3O plus concentration, this is the same thing. Okay, so just kind of allow those things to be interchangeable. With that being said, so when we have something acidic, these H pluses or these protons pop off into solution and they'll react with a protein in your tongue that gives the sensation of sour, like pings your nerves on your tongue. It actually sends an electrical signal, like a nerve pulse to your brain where you experience that. Acids will dissolve metals with enough acid. You would need quite a bit of acid to dissolve it. So here are some of the properties of acids. They have a sour taste, they dissolve metals, and they turn blue litmus paper red. I don't really care about this last one a whole lot. Litmus paper is a paper that is pH dependent, so its color will change depending on the pH. If you happen to have a specific blue litmus paper, it would shift red. Here's an example of an acid. HCl, this is hydrochloric acid. Simple, one of the simplest acids we have, right? Just a hydrogen here and then the chlorine. When this gets dropped into water, that hydrogen pops off. That is what gives it, the acidic quality. Hydrochloric acid is the main component in stomach acid. So if you ever have acid reflux or your stomach's kind of upset and icky, it's because this is coming up into your esophagus and throat. Your stomach lining is designed to hold hydrochloric acid. Your esophagus and your throat are not, so they are sensitive to it. Why do we have this stuff in our stomach? It is essential to kill bacteria in our food. Even food that you've cooked perfectly and you've cleaned every surface and done everything you're supposed to do, it still contains bacteria. The hydrochloric acid will help to kill that off before it gets into your lower intestinal tract. Like it says, that sour taste associated with indigestion is caused because of the stomach acid. Here's two other acids. These ones are a little bit more complicated. We've got sulfuric acid and nitric acid. If we look here, so this is H2. This is actually what's called known as a diprotic acid. It has two hydrogens. Here's one of the hydrogens. Here's another hydrogen. Whenever you have more than one hydrogen, the hydrogens don't all come off at the same time. One will pop off first, and then another one will pop off in a second instance of removing the hydrogen. Here's nitric acid. This is a monoprotic acid. It just has one H to it. There's the H. That thing is what will pop off. Sulfuric acid is the most widely produced chemical in the United States. Over 36 million tons of this stuff. We use them in lab settings. Sulfuric acid and then nitric acid, a lot of nitric acid is used in fertilizers. That's why it's so abundant in this country. We use a lot of fertilizer in this country. We produce a lot of food. Also, you can find these things in explosives, and then dyes and glue. Anything that's good for making fertilizer is also really good for making explosives, just FYI. Those two things kind of go hand in hand. Here are some even more complicated acids. This is known as acetic acid. This is a good one to look at because you can see there's multiple hydrogens in here. There's the hydrogen that's sitting in the front, and then there's these three hydrogens that are sort of buried into the molecule. This is known as the ionizing hydrogen. That's the hydrogen that will pop off in solution, okay? So the hydrogen written in the front is the hydrogen that comes off. The hydrogens that are buried in the molecule over here, those are not going to come off in an acidic way. So this right here, you can see the carbon and it has the hydrogens grouped on it. These are bonded. You're gonna have to do something much more chemically reactive to have those come off than just drop them in water. This hydrogen over here, this is our ionizable hydrogen. Acetic acid is an example of what's known as a carboxylic acid. This is getting a little bit more into organic chemistry, but this group, sometimes it's called the COOH group, COOH, or it's a carbon and it's double bonded to an oxygen and then bonded to an oxygen and a hydrogen. This is a very, very common grouping of atoms, a common functional group that we see in a lot of organics. Citric acid is an example of a carboxylic acid, so is malic acid. Both of these, if you look at this one, this thing has a total of 8 hydrogens, but how many ionizable hydrogens does it have in an acidic sense? Just one. This one over here has a total of 6 hydrogens, but only one of them is ionizable. That's the only one that would pop off and give acidic qualities. So something has to counteract this acidic nature in the universe on Earth, and that is a base. And a base kind of has the, I don't want to say it has the opposite properties, but it has properties that will balance an acid. So bases tend to have a bitter taste. Bases will feel slippery to the touch. And then if you had a red paper, litmus paper, it would turn it blue. All of these things here, all these cleaning supplies, tonic water, these all have bases or are considered bases. That's what gives them this slippery feel. Have you ever gotten bleach on your hand and it's like really slimy feeling? Or soap does it as well. And that property of it being kind of slippery is what makes it a good cleaning supply. So as far as bases, bases tend to taste bitter. Bases are less common in food products. We don't usually eat things with high pHs. We kind of have a natural aversion towards these things because bases a lot of times are a type of alkaloid, or it's an organic material that like plants will produce. It's toxic. Okay, so like hemlock, there's other ones out there, but the things that are poisonous tend to be basic in nature. It doesn't mean that there aren't things that we do eat that are base. There are a small amount of foods that we do eat that are basic. Choline over here is basic, and that is present in coffee and caffeine. So coffee overall, like as a whole, not because coffee isn't just 100% caffeine, right? Coffee as a whole is acidic, but caffeine is basic. So that's why you can drink coffee and it has sort of a bitter taste to it, but it gives you acid reflux because the flavoring of it is bitter from the caffeine, but the overall coffee product is actually acidic. So if you have an upset acidic stomach, you don't want to drink a bunch of caffeine, or you don't want to drink a bunch of coffee, rather. You'd probably be better off drinking some milk. So examples of bases, sodium hydroxide, potassium hydroxide, and then sodium bicarbonate. A lot of the bases that you will see have hydroxide. Hydroxide is not the same thing as hydronium. Hydronium is H3O plus. Hydroxide, remember from your polyatomics, is OH minus. Sodium bicarbonate doesn't have hydroxide in it per se, but it will produce a hydroxide ion, and we'll look at that a little bit later. Sodium bicarbonate is something that is contained in an antacid, like a Tums. So if you're having an acidic sour stomach, you can take that and that will help to neutralize or relieve heartburn. So there are quite a few ways that you can classify an acid and a base. For the sake of this class, we're going to go over two different ways of classifying it. The simpler way is what's known as the Arrhenius definition. And then a little bit more complicated will be the Bronsted-Lowry definition. So for the Arrhenius definition of an acid, this is kind of what you guys have maybe thought of an acid thus far, is that an acid will produce these H pluses in solution. So if I have something and I stick it in water, if it breaks apart and one of the things it breaks apart into is an H plus, we can check it off as being an acid. Okay, that's all you really need. So here is an equation. We've got this thing, it drops in water and it breaks apart into its ions. Remember, it's got that aqueous symbol. The aqueous thing is letting you know that it will dissociate into its ions. Because it's breaking apart into ions here, we could say that this is an electrolyte solution. There's a current that we can pass electricity through. We kind of already went over this. So H plus ions are highly reactive. So they will even react with water, right? This is a water molecule, oxygen, there's the hydrogens, there's the two lone pairs of electrons. One of these H pluses will stick to it and you get the hydronium ion. So H3O plus and H plus will always be kind of associated with each other. So let those things be interchangeable. You may see them written where the person is describing it as an H plus or they're describing it as an H3O plus. They're talking about the same thing, which is this production of an acidic thing. Kind of already went over this as well, but when we're writing a formula, here's formic acid. The ionizable hydrogen will be written in front. Non-ionizable hydrogens are buried somewhere farther in the molecule. When we're looking at a structure, if the hydrogen is connected to a carbon, that's non-ionizable. The hydrogen that's connected usually to an oxygen, this thing will be the ionizable one. But really this is more where I'll be testing you guys on. So just know if you see this thing, it isn't actually two ionizable hydrogens, it's just one ionizable hydrogen. So the Arrhenius definition of a base, I feel like the Arrhenius definition of an acid, like this covers a good amount of things. The Arrhenius definition of a base is this idea that a base will be anything that when you drop it in water, it'll dissociate into an OH ion. This definition misses so many things that are bases. So this is kind of why we've had to expand. But the simplified version is for the Arrhenius is that I have something and it has a hydroxide ion in it. When I drop it in, you will find an OH. So start getting comfortable. When you see OH, this is talking about a base thing that has base-like properties. When you see H plus or H3O plus, that's an acid. Okay. So if you stick something in water and you get that OH when it dissociates, you're dealing with a base. It is important to look at, it's got to be ionic. So it's got to be a metal with a non-metal. Something like this, where we have, what is this, methanol? Yeah, methanol. If I was to drop this in water, would this dissociate or break apart? No. Why? Because these are all non-metals. Okay, so yes, there's an OH, but these are all non-metals, so they're covalently bonded together. That thing is not going to dissociate in water. It's got to be something like this, where it's a metal with that OH polyatomic ion to be considered an Arrhenius base. This thing will stay together. It may dissolve in water, but it'll stay as a molecular packet. So, okay, so we've got this simplified definition. Under the Arrhenius definition, if we take an acid, and it doesn't really matter what the delivery system is, this could be, you know, HCl, writing one thing, saying another. It could be HBr. It could be H2S. Doesn't really matter, right? What this thing is. This is just delivering the important thing. The H is the star here when it's an acid. When it's combined with a base, and again, the OH is the star of the base. So it could be delivered with sodium. So it could be NaOH. It could be calcium hydroxide, CaOH2. It could be potassium hydroxide, whatever. The star is the OH. That's what's making the basic thing. So anytime you take a hydrogen or an acid and you combine it with an OH or a base, those two things are going to come together and make water. Water is neutral, right? We think about pH of 7, something being neutral, we're going towards a water property. So this is what we would call the net. Remember net ionic equation? We're taking out any spectators and we're just looking at what the important reaction is. So something acid, something base comes together to produce neutral water. Yay, we understand acids and bases. Well, sort of, but this doesn't cover all of the acids and bases. So under the Arrhenius definition of acids and bases, we cannot explain why some substances act as a base, even though they don't contain OH. So an example, NH3. Okay, this is a base. Does it look like a base under the Arrhenius definition? No, there's like no OH anywhere. It doesn't look anything like a base, but it is in fact a base. So we have to expand our understanding of what an acid and a base is doing. So in general, the Arrhenius definition does not apply to non-aqueous solvents. We have this expanded definition, which is known as the Bronsted-Lowry definition of acids and bases. In the Bronsted-Lowry definition, we are going to instead talk about the transferring of H+, or you may hear somebody say the transferring of a proton, because H+ is just a proton, right? Or you may hear the transferring, well, it'd be H+ or proton. So instead of putting H+ in solution or putting OH in solution, we're now going to be talking about acids and bases as being either a proton donor or a proton acceptor. So an acid is anything that's a proton donor. It will give an H+ up. It doesn't mean that it puts it into solution. It just means that it's giving it up. A base is going to be a proton acceptor. It's going to take a hydrogen. It doesn't mean that it's going to break apart and make OH in solution. It will still produce OH, but it's going to do it by stealing a proton. And I'll show you guys this in a minute. Why is it called the Bronsted-Lowry definition? It's because simultaneously two dudes in like 1923, one Bronsted, one Lowry, came up with this same definition independently, but simultaneously at the same time. And that actually happens quite often in science. You will hear about two people on the opposite sides of the world from back in the day making the same discovery like within a week of each other. Just sort of happens that way. So let's look at this. So when you see this right here, you're probably already like, oh, I know that's an acid. I don't need to like really go through this whole process. Well, but we still want to be able to, because sometimes they don't look so blatantly acidic. So how I do this is I find the pairing on the left and the right side, or the things that look like each other but are separated just by either an increase in a hydrogen or a decrease in a hydrogen. So this thing and this thing over here kind of look like each other, right? This is a chlorine with a hydrogen. This is just a chlorine. So I'm going to pair those guys together. Then I'm going to pair this and this together. This is H2O, this is H3O. So these are similar in appearance, but this is just up a hydrogen. So when we are describing what's going on here, we'll match these up and then look at what the change is that happens. So what happens to the HCl here to become Cl? What does it have to do? It has to donate a proton. So this is a proton donor, okay? If you're a proton donor, by the definition, you are an acid. Dun, 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 you're an acid. Because remember, we go back here, an acid is a proton donor. A base is a proton acceptor. So here we go. So we got a proton donor. That means, okay, well, what is the water doing here? The water is a proton acceptor. Do you see that? How the water went from H2O to H3O? So this is a proton acceptor. So that makes water here a base. Water is known as amphoteric, and there's a slide on this a little bit later on. It means that water can behave either as acid or a base, right? Because it's right at a pH of 7, it's easy for it to take on the properties of an acid or a base. In this situation, because HCl is such a strong acid, the water is going to behave as a base. So, you know, you may look at this and say, well, that's easy. I can blatantly see it's an acid. I don't need to go through this whole process of the Bronsted-Lowry, but let's look at something that isn't so obvious. Okay, let's look at this thing here. So I told you all that NH3 is base. When you look at it, does it look like a base? No, it doesn't look like NaOH or CaOH. It doesn't look like something that's going to make OH, but it actually does. So let's pair them off. So we've got this thing here, and that looks like this here, right? Just separated by an H. And then this H2O looks like OH minus a hydrogen. So what is the NH3 doing to become NH4 plus? It is a proton acceptor, right? What is the water doing here? It's a proton donor. So if you're accepting a proton, that makes you a base. If you're donating a proton, that makes you an acid. So this thing here, ammonia, it stole a hydrogen from the water. This thing grabbed one of these hydrogens to make the NH4 plus, and what was left? OH minus. This is what makes the final solution basic. Right? This thing is the basic quality. So instead of breaking apart to make OH, it stole hydrogen from water to make OH. So we would classify this thing as a base. Do you notice how this changed? It increased the number of hydrogens, right? If it's a proton acceptor, it's going to go from 3 to 4. What happened to its charge? Over here, the charge was neutral. Over here, the charge went to a positive. Why did the charge go up? Because it's not just hydrogen, it's hydrogen with a plus charge. So we have to take into account that positive. What happened to the water? Here, the water has a neutral charge. We got rid of an H, and we also got rid of the plus. So that's why the charge went down to a negative. Neutral, take away a plus, you get a minus. These are known as acid-base conjugate pairs, or Bronsted-Lowry acid-base pairs. And we will do a little bit of practice on how you can predict those or make those. So this is sort of everything we already talked about. So there is an acid. If one thing is being the acid, the other thing is being the base. This grouping or coupling is known as the conjugate acid-base pair. So if this is a base, I said this was the base, its buddy over here is going to be known as a conjugate acid. The equation has a double arrow because this thing is happening in the forward and reverse direction. So I could flip this equation around and put these as the reactants and these as the products. And then if we're going in this direction, what is this thing having to do to become this? It would have to give the H to become this. That's why this is the acid, okay? So base and acid will be on the reactant product side. Conjugate acid base will be on the, acid base will be on the reactant side. Conjugate acid, conjugate base will be on the product side. It's always going to be paired opposites. Okay, so base will always be with a conjugate acid and acid will always be with a conjugate base. We'll never have a base with a conjugate base or an acid with a conjugate acid. That doesn't work to flip-flop the equation. You will have to like be able to identify these in an equation. So if you can get one of them, all the other ones fall into place really easy, right? Let's say you knew this was a base. Well, this thing has to be an acid. And if this is a base, its buddy has to be the conjugate acid. And if its buddy is the conjugate acid, the other thing has to be the conjugate base. So you kind of fill them all in. So we call these things, I was saying this is a base and this is a conjugate acid. These are conjugate acid base pairs. What makes a conjugate acid base pair? You're either going to increase hydrogen by 1 or you're going to decrease hydrogen by 1 and adjust the charge accordingly. So here's an image of that NH3. Its conjugate acid would be NH4 plus. We're adding a hydrogen, up the hydrogen, and up the charge by 1. The water, which is, it says it in this slide over here, is amphoteric, meaning it can be an acid or a base, depending on the situation it's in. In this case, it's acting as an acid because the other thing is such a strong base, or a stronger base than water. If it's an acid, we're going to take away a hydrogen with a plus. So we go from H2O, neutral charge, rip the hydrogen off, drop the charge down. My goodness. It's 10:06. So it's my daughter's first birthday today. So I was like in labor giving birth literally a year ago because she was born at 10:10. So it's crazy. You totally forget about all that. You forget how much work that was. And so you'll do it again and again. My husband won't let me though. He's like, 2, we're done, no more. Okay, so let's look at this guy here. We have H2SO4. It's combining with water and, thank you. It's combining with water to produce this HSO4 minus and H3O plus. So they've already paired it off for us. I'll have you guys do some of these that haven't been done for you. So we've got this thing paired with this thing, and then this thing paired with this thing, right? Does this look like an acid? It actually looks like an acid, right? Because there's an H in the front, and it is in fact an acid. But let's go through the process of what's going on. So to get from here to here, we drop a hydrogen and we drop the charge. If we're losing a hydrogen, that makes us an acid, right? Because acids are hydrogen donors or proton donors. The water, well, the water is gaining a hydrogen. Went from a neutral charge to a positive charge, and we increased the hydrogen by 1. So that makes this thing a base. And then we just pair, acid with a conjugate base, base with a conjugate acid. So I want you guys to do one of these on your own. No, okay. I can't really think of one off the top of my head. Come up with an equation for y'all. Okay, so we're gonna do, I'll give you two. I'm gonna write out the equation for you. I want you to tell me what's acting as the acid and the base and what's its conjugate acid and its conjugate base. So we've got CH3COOH. This is known as acetic acid. We're combining it with water, and these will be our products. CH3COO minus plus H3O plus. That plus, that's a charge. So pair them up with their buddies, see what they're doing to get to that product, and then classify acids and base from there. Let me give you another one too. Come on. This one, H2O plus HCO3 minus OH minus. Okay, there's two there. So right now, just labeling what's the acid, the base, which the conjugate acid and the conjugate base. Just another 30 seconds there. Okay, so, you may be looking at these and especially this first one, you're like, that's really scary looking, right? I don't know what that compound is. It's okay. It's acetic acid. I wouldn't expect you to have that memorized, but you still should be able to decide if it's behaving as an acid or a base, because at the end of the day, what you're doing under the Bronsted-Lowry, you're going to pair them up. This thing and this thing definitely look like each other. This thing and this thing look like each other. Okay. How do I get from here to here? I have to donate, right? Donate an H plus. It's lost a hydrogen. It's doesn't have the hydrogen written in the front. I know that that's a little weird. It's at the end. That's just because it's drawing it sort of structurally, but it's still losing the hydrogen. So we lost the hydrogen and we went down in the charge. So that makes this thing an acid. Everything fills in really easily from there. If this is an acid, this is the conjugate base. If this is an acid, this has to be the base. If this is the base, this has to be the conjugate acid. Right? If you can get one of them, they all fall into place. And if we want to go conceptually through what's going on here, the water is taking on a hydrogen and increasing the charge. That makes it a base, a proton acceptor. Let's look at this thing here, water combining with, this is known as bicarbonate to produce OH and H2O plus. So we need to pair them off. So this looks like this. This thing and this thing are similar to each other. How are we going from there to there? We are accepting an H plus. What is an H plus acceptor? That is a base, right? That makes this the conjugate acid. If this is a base, that means this has to be the acid. Is it in fact doing what an acid does to get from there to there? Yeah, it's donating an H plus. So that makes sense that this is an acid and this is a conjugate base. You're done. Yes, no, maybe so. How's that feel? Good, okay. I'm gonna give you a couple things. I want you to tell me what is the, right, I want you to write the conjugate base. Okay. So H2SO4, HCl, yeah, do those two. So write a conjugate base for these acids. These are both acids. Ask yourself, what does an acid have to do to become a conjugate base? Okay, so if we're an acid and we want to become a conjugate base, we have to donate a hydrogen. We donate a single hydrogen. This has two, I know. They're going to come off one at a time. So we're going to drop the hydrogen. So instead of it being H2, it'll just be H, SO4. And what do we have to do with the charge? It was neutral. Now we've got to make it negative. How about HCl? We're going to ditch the hydrogen. So we'll have chlorine. What do we do with its charge? Make it negative. So this would be the acid, and these would be its appropriate conjugate base. If we were to go the other way, I'll give you one. So let's say we've got, what do I want to do here? Okay, let's do water. H2O and HS minus. Okay, these are the bases. I want you to tell me what are the conjugate acids. Okay, I'll give you the base, you tell me the conjugate acid. Give you just a minute for those. It's the opposite of what you did in the last set. So for these, if we want to go from a base to acid, we're going to add an H plus to both of these, right? Because they're proton acceptors. So H2O will become H3O plus, right? Which again, this thing is like synonymous with an acid anyway. So that kind of makes sense. What are we going to do here? HS minus. If we're going to add an H plus to it, it'll become H2S or hydrosulfuric acid. Y'all feel good with Lewis or Bronsted-Lowry acid base, conjugate acid base pairs? It's just this sort of transferring of hydrogens. So this will allow us to explain a lot more things in their acidic and basic properties. Are there other definitions of acids and bases that get more advanced than this? Definitely, but this will cover us for our class. So this isn't anything new, but reactions with acids and bases, we can have what's known as a neutralization reaction. So a neutralization means that you're neutralizing either an acid with a base or you're neutralizing a base with an acid. It's when you take an acid and a base, you bring them together and you get water and a salt. Remember that this is kind of like a double displacement. The hydrogen combines with the OH to give you the water, and the remaining metal and non-metal that were delivery systems for the acid base will produce the salt. The net equation is this thing down here. So we've got a hydrogen plus an OH, a hydroxide, to give us H2O. And we have a neutral pH. There are some neutralization reactions that are a little bit more complicated. If the reaction contains what's known as a carbonate or a bicarbonate, we will get, and so a carbonate or a bicarbonate has that CO3 in it. If we have an acid combined with some sort of bicarbonate, we will get water, we will get our salt, but then we also get CO2. Okay, and that's why they fizz. So if you take, and this is an example of a gas evolution reaction, again, which we covered a few chapters ago. If you've ever taken like a Alka-Seltzer, you put it in the water and it'll fizz up for you. Okay, so just going over some properties and what the equations look like. So acids react with metals in a way that causes the metal to go into solution. So why does an acid make a metal dissolve? It almost looks like the metal disappears. Well, it's not actually disappearing. What's happening is we have an acid, and then we have a metal which is in solid form. So these are what we're starting with. When we put those things together, we get a single displacement reaction, or the solid metal is very much attracted to the delivery system of the acid, the chlorine. This is so attracted that it actually changes state. It goes from a solid into an aqueous form. So it has shifted from a solid form into a dissolved form. The metal is now in a dissolved form. What happens to the hydrogen that got kind of booted? That will turn into a gas, so it fizzes. So that's why when you put metal in acid, You'll get all this fizzing. That's the hydrogen bubbling off. And then the metal is combining with the chlorine to give us something aqueous in nature or dissolved. And that's sort of the gist of any sort of metal getting dissolved. If we look at some other ones here, here's acid with magnesium or with zinc or with metal. What are you getting in every single situation? You're getting the hydrogen coming off as a gas. And in each scenario, the solid metal is combining to form an aqueous salt that can dissolve in the water. And it appears as if the metal has disappeared. It hasn't disappeared, it's just gone into solution. Wouldn't work with gold. Not really gonna go a whole lot into this. So I'm just gonna skip over the whole talking about reactions with metal oxides. Reactions of bases, neutralization, reaction. We're not gonna go into that. We're not gonna do the alum reaction, so we'll skip over that. But I do want to talk about titrations. This is sort of an expanded, it's not even expanded, it's the same thing as solution stoichiometry. So remember last week when we did the solution stoichiometry, compound A, compound B, volume into moles into volume again? That's the exact same thing that we're going to be working with titration. So a way to quantify the amount of acid or base in a solution. So we use solution stoichiometry in a titration. What is a titration? In a titration, a substance with a known concentration reacts with another substance with an unknown concentration. So it's sort of like we have an acid, let's say, and we don't know what its concentration is. We want to figure out its concentration. Well, we can use a known concentration of base, add the base until we get to a neutralized equation where it's all the acid and base have balanced out. Once we've hit that equilibrium point or titration point, we can then run a calculation. So here is a hydrochloric acid solution, and we've got these little H pluses. The chlorines and the H2O molecules aren't involved in the reaction, so we don't have them. Those are like in the liquid. Okay, we're just not going to look at those. But we've got these little H pluses. In a sample of titrate, when we're titrating, so we have an unknown amount or an unknown concentration. I don't know how concentrated this is. So I take a known amount of a base, and the bases have little OHs. I start just very slowly dropping some of these OHs into the unknown concentration. And what are the OHs going to do? The OHs are going to naturally pair with the hydrogens to form water because they're going to neutralize. So this little guy is going to like bond to this guy to form a water. So at a certain point, I will have added enough of this known amount to pair every H plus with an OH. Or we get this here, which is known as a neutral solution. Right, it'll have a pH of 7. And everyone is paired off to make little water molecules. So I've dropped in a certain amount of these. I know what the concentration of this, I can work backwards to find the concentration of the unknown. How do you know you've reached your equivalence point or your point where the acid and the base are equal to each other? Usually you add an indicator. In this case, we use phenolphthalein. It will turn slightly pink when it's reached a pH of 7 or when it's all the acid and all the base are equal to each other. So yes, we've got, let me see the picture. Okay, so it'll look like this. So I've got an unknown amount or an unknown concentration in here, a known concentration in here. I start opening this valve here and dropping base in. It'll turn pink for a second and then the pink will disappear. You keep adding it until you get to a very faint pink color that stays. That's when you know that your acid and your base are equal to each other. That's conceptually what's happening. Let's look at a calculation or an actual problem. It's just solution stoichiometry. So it says the titration of 10 milliliters of hydrochloric acid solution with an unknown concentration, so we don't know the concentration, requires 12.54 milliliters of a 0.100 molar NaOH solution to reach the equivalence point. The equivalence point is the neutralization point. It says, what is the concentration of the hydrochloric acid? So it doesn't give us a balanced chemical equation in the problem. I'm going to write a balanced chemical equation for this. It's a neutralization reaction, which means we're taking an acid, HCl, we're combining it with a base, which is NaOH. What do we always get in a neutralization reaction? We're going to get water, H2O, and we're going to get a salt, which is the leftover stuff, so NaCl. You balance it, and in this case, it happens to be a 1-to-1. It'll be one of these for every one of those. So solving this is just like your solution stoichiometry. I want you to figure out which one is compound A, which one is compound B. Compound A will be the thing you have more information on. Compound B will be the thing you have less information on. I want you to try and solve this. It is just solution stoichiometry. Okay, so if you want, you can revisit your notes from last week and use that to get you through. I'll give you all 5 minutes to solve this. Make sure you're checking units, milliliters. We don't really like milliliters, okay? Sorry, I'm just going to type this out in here. So give me a second if you lose the problem for a minute. Just another minute to finish up your thought process, and we can go over it. All right, so when looking at these problems, compound A is going to be whatever we're trying to, or the one we have more information on. So NaOH, we have two pieces of information on. We know its volume, which is 12.54 milliliters. Because I'm using molarity, which is a mole per liter unit, I'm just going to right away get that into liters. So move the decimal over 1, 2, 3, or 0.01254 liters, small amount. The molarity on this thing is 0.100 big M. Again, for dimensional analysis, I don't like it written as big M. I want 2 units. So I'm going to say 0.1000 moles. I think I have too many zeros there. Drop one of those. Moles. This whole thing. 0. Moles specifically of NaOH for every 1 liter of the NaOH solution. For compound B, that's what I'm trying to find information about. So HCl, I know its volume. I know that I had a 10 milliliter sample, 10.00 milliliters. Let's change that into liters. So 0.01000 milliliters. I'm sorry, now we're in liters. And then it wants the concentration. So I need to find the unknown concentration. Well, concentration equals molarity equals moles over liter. Do I know the liters for this? I do, it's right here. So I can actually let's just put moles of HCl over what the liters are. And the liter is right here. So 0.01000 liters. So I need to solve for moles of HCl. Well, remember that flow chart from solution stoichiometry that told us that we can go from volume of A into moles of A into moles of B into volume of B. We're going to start with volume A. We only need to get to moles of the second component, right? So we're going to stop right here. So we actually only have to do 2 hops. We don't have to do the final one, so we can just sort of cross that out. So start with our volume A, and if you've done this, it should be really easy to kind of thread this all together. So volume A is 0.01254 liters of the NaOH. To go from volume A into moles of A, this is where you have to use the molarity. Specifically the molarity of A. So I'm going to use it just as it is. I like it like this, as opposed to flip-flopped, because the liter will be on the bottom and the mole will be on the top. So we get 0.100 moles of NaOH for every 1 liter of the NaOH solution. That will allow liters to cancel out and we'll be left with moles of NaOH. Now, how do we get from moles of A into moles of B? That's the stoichiometry. That is using the balanced equation to figure out the ratio. So it's a 1-to-1 ratio. Is it always going to be 1-to-1? No. So make sure you take into account if it was a 1-to-2 or if it was a diprotic acid. But in this case, it's 1-to-1. So we get 1 mole of NaOH will always yield 1 mole of HCl. Can we stop there? Yeah, we can pause there mole, because that will give us moles of HCl. Our final unit right here will be mole of HCl. So let's go ahead and calculate that out. We're dealing with small numbers here. So if you're getting lots of decimals and stuff, that's okay. So 0.01254, we're going to multiply it by 0.100. Everything else is ones, so we can kind of just like leave those. So I got a number of, real small number, 0.001254 moles of HCl. Am I done? Not yet. What's the final step? We need to take this and we just have to thread it back here because we're actually trying to solve for the concentration. Okay, so take your molarity, or rather your moles, and divide it by your volume, which was 0.01000. And I get a concentration of 0.1254 big M, meaning molarity, moles per liter. Let's make sure that I didn't mess that up somewhere along the lines. Yeah, they rounded to 3 sig figs, so 0.1254. You all seen how that's the same thing we did last time? It's just, they're just saying it's a titration problem, but it's simply a stoichiometry problem, a solution stoichiometry problem. Okay, so follow the same system, figure out your compound A, your compound B, organize the information really nicely, and then follow the flow chart, volume A, moles of B to volume B, and stop where you need to. All right, and that means we are going to stop here. So that gets us through the first part of this chapter. The second part of this chapter, we're going to talk a little bit about strong acids and bases, and then we're going to get into some more calculations with like pH. What does pH mean? How to calculate pH from concentrations and things like that. So yeah, y'all are good to go. If you've got any individual questions, stay around. If you've got a general question, just throw it out there right now. Turn your mute off. Otherwise, I will see you on Wednesday. Bye, everybody.
My only question is, I think I asked you this before, but any